some instructors, I mean, it's rightfully so, logarithm is an exponent. The reason why they say it. Yeah, if I'm trying to get y by itself here and say I did, because apparently I can, because it's a function, supposedly I can. And to try to do it by inverses, it's just not happening. You know, inverses you guys had, what do you, swap the x and y, solve for y kind of thing. This is like solve for y, I don't know. Turns out that this is whatever happens here, y equals, oh, here it is the inverse of f of x equals 2 to the x. So this y, if I can get it by itself, is an exponent. See how that's an exponent? That's why they say logarithms are exponents. But in any case, read. You can read all this stuff on your own. Who John Napier is. Sometimes they called it Napier's bones. You know, that's a little historical thing you can read about. What's Jeff talking about? Napier's bones. Euler. Now you've heard of a mathematician named Euler. I said it wrong. Every once in a while I'll do that. It's Euler. It looks like it's Euler, but it's not. So Leonard Euler, Euler's number, the natural number, we talked about that. Looks like this. E is the natural number. So somehow he's connected to it, logarithms. There's a base 10, by the way. Base 10 is called common logs. Base E is called natural logs. So base 10 common logs. Natural logs is a base E. And even says, you know, where is it found? You can take a look at, Google it, find out how logarithms base E, natural logs, are really used and why. It's found, probably logarithms found that makes sense to me is Richter scale. Richter scale. It's a device, probably by Mr. Richter, that helps predict or understand earthquakes. So logarithmic scales is used for that. So that picture, that's right here, is the picture of the thing that I drew today's Wednesday? Yeah, 2 days ago. No, today's Tuesday. Last Thursday. Okay, this picture right here is that picture right there. All right, 1042. 1042. Okay, so 1042. It's the same picture, so we're calling it logarithms. Notice the base, that's 2. Okay, it's the same concept as the base is 2. And so when you get here, to solve for y, you know it's a logarithm. So log base 2 of, it's an argument. Logarithms have an argument. Oh, trig, for next semester, for some of you, we'll have something called an argument. Y equals log some base. What goes in here is called the argument. Let's see, trig. Y equals sin, sine, not sin, sine. That's also called in there, inside there, whatever it is, it's called the argument. Let's see what else currently. I think those are the two more famous ones, is the trig, and then of course you've seen logarithms. I don't know how many of you remember your instructor saying it's the argument for this, but now you've heard me say it. Okay, this is read as log, I say base, so log base 2 of, now that's not multiplication. That's the argument. So log base 2 of x. Do you read this as f times x? You don't. No. F of x. Don't think of the word of as multiplication in this context. I mean, sometimes it is. Take half of 4. Well, half of 4 is 2. It's 1/2 times 4. But with function notation, of does not mean multiplication. So of does not mean multiplication. So log base 2 of x. Sometimes they'll say log 2 of x. Log 2. They'll just kind of butcher it up or shorten it. This is a formal definition. Formal definition. So yeah, he said logs and exponent. Looking to see what the author says about. Yeah. Does he say logs and exponent? I mean, I'm curious now. Earthquakes. Remember I said earthquakes, Richter scale. Richter scale. They do a review for you. This is all for you right here. It's in your textbook. You pay good money for this textbook. Might as well go ahead and skim through it. It's a good thing. My packet gets you by. But if you really want to be, top student slash you want to understand it absolutely the best, then you use as many resources as possible to really master the material so that when it gets to calculus, you've got enough to struggle with in calculus. It's a completely different creature. To use everything we've learned or learning here, why not try to get as close to mastering the material? I'm still learning. I mean, it's been 2 years since I've done a course like differential equations. I'd have to reteach myself and watch some videos, and oh yeah, it's starting to come back. See, I haven't taught differential equations for a long time, and it's just the way it is. So when you don't use it, you sort of lose some of it. So I use what they've given you. That's my suggestion. Definition. Okay. See, they're trying to go through inverse concept, and let's see. Oh, here, formal definition. Right. I just wrote mine slightly different. I think it's about the same. So if you look at my packet, it'll feel similar to this. What was I looking for? Log. Do they say it's a log as an exponent? That's what I'm looking for. I'm looking. Oh, okay, there it is right there. It's right, staring me right in the face. It's an exponent. He says the same thing. Turns out for logarithms right here, for that one, domain would be all, well, the domain is over here. Look, right there. There's the domain right there. That's the argument. Y equals log base A of X in this case. The domain is X, so it's greater than or equal to 0. Look at the picture. It can't be equal to 0 because it's not hitting the y-axis. So it's greater than 0. The domain would be 0 to infinity. unless you have something that looks like this. If you had something that looks like y equals base, oh my gosh, not base b yet. Where's my whiteout? There's one here. Oh, there it is. That's right. What if I had log base b of x minus 2? Well, the argument right here indicates or determines what your domain is. So if you just like square root, okay, here's an idea. F of x is equal to square root of x minus 2. You can't use a 2. See, this one's familiar. You can't use a 2. So how do we do it? We take this, we take x subtract 2 and say it's got to be more. Well, actually, you could use a 2, my mistake. You could use a 2, but you can't use anything less than 2. And you solve for x. Same thing here. This here, so x subtract 2 has to be bigger than 2. It cannot be equal to. Oh, some of you don't know. Here, watch this. Log, LOG. Okay, what I just pressed was the LOG button that's right down here. That's the log base 10. That's log base 10. It's called a common log. This one right here is a log base E. That's a natural log. So these are two special buttons. I did log. There's an invisible 10 down here on the bottom. You just can't see it. Jeff, what about log base 2? I'll show you how to find that with the calculator in a moment. Anyway, log base 10. If I put in 0, the calculator is going to say, yeah, you can't. You can't take log. The x value cannot be 0. The argument ultimately can't be 0. You'll get that. Yep, undefined. No. So right now, I can't use the number 2 because that'll cause that to be 0. I can't use 2. Nor can I use like 1. Okay, watch this. LOG. How about 1 subtract 2? 1 subtract 2. If I put a 1 right there, 1 subtract 2, it'll say, nope, not real. Nope. What if I put a 3 right there? 3 minus 2, it's 1. 3 minus 2. So log 3 subtract 2, it's 1. Okay, it's something. How about if I put 2.5? I went 2.5 minus 2, 2.5 minus 2, which is still positive. That's what I'm saying. It's still positive. As long as it's positive, you're good at the end. Log 2.5 subtract 2. Still okay. I'm getting an answer. What about that ln thing, Jeff? All right, well, do the same thing. Go 2.5 subtract 2. You'll get something. Won't give you the same thing, but you get something. How about ln and do that 2 minus 2? No, it's going to give you error. Yep, error. So for this one here, it's based on the argument right here of just being x. That's from 0 to infinity. Range is all real numbers. X intercept right here is going to go through 1 on the x-axis, and you'll say none. Okay, log base 10. Well, see, the base has to be some special numbers as well, by the way. The base can't be a 1. Okay, look back at the formal definition, previous page. See, the base can't be 1, and the base also has to be positive. It just can't be 1. But this says the base could be a fraction. That's true. The base could be a fraction. Let me show you in your calculator where you find the bases. Now, I've got an 84 plus. If you've got an 83, you won't have the what I'm about ready to show you. You don't have it. 84, all the 84s do. If I go into, I think it might be one place might be math. I'll try that. math, and then toggle down. I went math. I went the math button right there, and I toggled down right there, that one there. If you got log and then base and capitalized, at least in my calculator, then you have probably something that looks like that, which is slick, because it allows you to type in any base that you want, any base that'll work. I'll do that again, math, toggle down, keep going, keep going, keep going, right there. And so I said a fraction. I think I said a fraction, just as long as it's not 0 and not 1, not negative. Let's do 0.5 as a fraction, half. Shoot, I forgot to type in something else. Sorry. Come on. Okay, now, so log base a half of, let's just put in a number 10 in there. Just anything. Yeah, okay, sure, no problem. What if I did instead of 0.5, I went -5. Remember, the base can't be negative. Let's see what happens here. Yep, didn't like it. Didn't like it. What about 1? I'm curious about 1. I haven't done this for a while. If I make that a 1. Yeah, I didn't like it. So this one, called a common log, if I want to change it to what's called exponential form, now that's what some of the problems you're going to be asked to do in your homework. This is called log form. Of course it is. I mean, it looks like log. This is log form. FOR. Okay, exponent form or exponential form. Okay, here it comes. I'm going to show you something here for a second. Back of the definition again. See, this is log form. This is exponent form or exponential form. Exponent form. So you're going to be asked to take something that looks like this, make it look like that. See the positions, it's all about positions. The position of the X has nothing to do with anything except by itself. So the way I start remembering it, the easiest way for me, that's a base. So that's a base. Of course it is. That's a base, that's a base. So if I'm going to convert this into exponent form, 10's the base. Oh, okay, 10's the base. That holds a power. Now the power is I got to either be X or Y. The power has to be X or Y. It's either 10 to the Y or 10 to the X. Either 10 to the Y or 10 to the X. See the M is the thing that's sitting all by itself. Or you see how these are connected? That's the other way. These are connected on the same side. X and A are not connected at all over here. The way I remember it is, hey, these are connected here. I don't make it 10 to the X. I don't make it 10 to the X. It's got to be the other thing. It's got to be 10 to the Y. And the only other piece is missing is the X. The graph of this is the graph of that. The graph of this as a table of values looks like, here's your X and here's your Y. Put in a 0 and you get a 1. Put in a 1. For y, you get a 10. You put in 2 for y, you get 100. Oh, shoot. Let's put in a 0 for y. Put a 0 for y. 10 to the 0 is 1. Put a -1 for y. -1. 10 to the -1. 10 to the -1 power is a 10th. Is a 10th. I just made a table of values for this. So my claim is when I plot this, it's going to look like this, because how do I make a table of values for this if you've forgotten from last semester? How do I do this thing? And then we'll look at the table of values in your calculator on this and compare it with what I'm doing by hand. So if I did that and plotted 1, 0 would be like right here, and 10, 1, which would be right here, and 100, 2, can't do that one. I did this one already. Oh, that's funny. Okay, fine. Oh, let's see. This would be x is -1/10 and y is -1. So it's like here. So if I plot those points, which I did, and connect the dots, do you think it stops right there? You think my red line stops with connecting those 3 dots? Nope. So what do? You put an arrow right here, maybe. Okay, you put an arrow. Do you think it goes through this way? It does not. We talked about that last Thursday. Yeah. I even just had a picture of it. Look at this thing. Look at this thing right here. Yeah, right here. It doesn't go through. It does not go through. Same thing with logarithms. It doesn't go through. So you're just learning this, or relearning, I should say. Well, how do I know, Jeff? Well, then take -8 right here. 10 to the -8. 10 to the -8 power is 1 over 10 to the 8th. This is 1 over 10 to the 8th, which is super duper small. The x value is extremely small, but positive, and the y value is -8. So you're way down here. See, so you gotta turn it, go like this, go down, put an arrow, and that is the picture I'm looking for in my calculator. Picture. Now, can I put that right there in my calculator right here the way it is? But what we could do is put this in your calculator, put that in your calculator right there. Graphing it. I'm talking about graphing it. Okay, log 10. Now you could go log base 10. You could do math, go down here, it'll work for everything, like here, and just literally type in the 10 right here. You could do that. And then you put in an X. That'll work. You don't need to if it's log base 10. You got a special button right here, special button that'll serve the purpose, but I'll leave it like that. And then I'll do zoom standard. And it looks like it stops, and you guys know it does not stop. And so what about a table of values, Jeff? Okay, sure. Yeah, okay, so X can't be 0. We knew that. X couldn't be 0. It bent right here. 1, 0, X is 2. Okay, what the heck? X is 10. Oh yeah, X is 10, Y is 1. We got that right here, right there. So that's images, or an image of the logarithm. And if I did these two, all you do is just put in a calculator and see what happens. Remember, this is a shift to the right. This is transformation. This is a shift. Right by 2, and this one's a shift down. Shift right 2 and shift down 2. Okay, if I did this one, my calculator, let's say I just used the plain old log button. Log. See, log base 10, just plain old log. You don't see the 10. It just does not appear. But it's there. If it's invisible, it's a 10. Okay, so I'm going to go with X subtract 2. Zoom standard. Looks like it stops there. No, it doesn't. No. On your group quiz, I said this last week. I know I did. Listen to my video. I said if on the group quiz, if you're just copying, if I said produce the graph and label or plot at least 3 ordered pairs, plot 3 ordered pairs and produce the graph. Okay, you can plot points. I get that. But if you make it look just like the calculator right there without putting in the turn in the correct look, the turn, and then putting arrows on it. If you don't do this, if I can make my red, you will not get credit for the graph at all. Because all you're doing is you don't get it. You're not, if you just give me this right there, you're not getting what I'm saying, or you're not paying attention, or you don't understand it, and you're not asking questions. So just beware, group quiz. Now on the exam, I'm not looking, you're not going to produce the graph by hand. You're going to pick the correct graph. If I give you this problem on the exam, looks like this, I'll give you a little bit more complicated one, but something like this. Pick the correct graph for this right here. And then you'll have A through D to pick. Probably a little bit more interesting would be, what's the domain of this graph right here? What's the domain? That's more interesting because I'm seeing if you get it. So if I looked at this and if I went and say, well, okay, I can see that. I can do a table of values, Jeff. If I plotted that, okay, 3, 0. Okay, I can do that one, 3, 0. Oh, but Jeff wanted an ordered, Jeff wants 3. Oh gosh, how about that weird one? How about 6, 0.6? 6, 0.6. 6, 0.6. Okay, right there. Gosh, I don't know. Let's see if there's any nicer ones out there. Oh, 12, 1. Well, that's way over here. That's like 12, 1 like this. Okay, there's 3, Jeff. Well, what do you want me to do? Well, connect the dots. Okay, there you go. No, that's not what I meant. Oh, yeah, okay. But it looks like that, Jeff. You're not getting it. I know it looks like that, but that's not the graph. Bend it. Okay, there, I bent it. Bad graph. Not doing that. Bad graph. Bad dog. There's like an asymptote right here. So this has to bend on this side. So more interesting might be either asking you to describe the transformation. There's only one transformation. It'll be shift right. What's the domain? D for domain. D for domain. What's the domain? Well, it doesn't look like it's going to the left of 2. Looks like it's 2 and getting bigger. And what's the range? All real numbers. And so on. You can do this one on your own. It's just plotting points and seeing what the curve looks like. All right, you'll have some problems that will be like this, where it's going to say, okay, here's the exponent form, make it into the log form. Here's the exponent form, make it into the log form. See, this is what the log form kind of looks like. There's a log, there's a base, there's an argument, there's an equal sign, and there's something else.
Hey, Jeff.
Yes, sir.
A shift up and down, or a shift up or down, is not going to affect the asymptote, right? The vertical asymptote.
That's correct. That's correct. Very good. Yeah. Good observation. The up and down does not affect the asymptote. It's only the left and right.
Okay.
Even the vertical stretch and shrink. Remember that? Vertical stretch and shrink, and even the vertical, or the what do you call it? The x-axis. Shoot, what do I? Reflection. Looking for the word. The reflection, the stretch and shrink, none of that. The only thing it does is the left and right. Yep.
So we always just assume that the vertical asymptote is going to be x equals 0 unless there's a shift left or right.
Okay, let's try this. I like your observation, or even your wording, Devin, the vertical asymptote. So let's see what the vertical asymptote, what you would do to find that, that wall, vertical asymptote. How might you describe to anybody else to find it? There's arguments different. So here's the argument up there. Nothing in the argument there. So there's no shifting left and right here. There's a shift right. How do you figure out the shift?
Left 2.
Almost. I threw a curve at you. You see this extra right here?
Yeah.
Yeah. So if I did this one, you see how this would be x minus 2 just can't be, or let's say it's equal to 0. Just set it equal to 0, then it's going to find the asymptote, the vertical asymptote. X equals 2 is the vertical asymptote. So if I did this the same way, 3x plus 2, set that equal to 0, is the vertical asymptote. Because you've got to solve for x. Vertical line is a x equals. This will be x equals negative 2 over 3. You got to move the 3 as well. Your class, I didn't have a numerical coefficient in front of the x ever for the shifting. So I just threw you a slight curve ball. The 3, you see the 3 right here? That, the thing I told you guys to disregard back in chapter 1 was the horizontal stretch and shrink. Horizontal stretch and shrink. That's what the 3 is kind of affecting, is the horizontal stretching and shrinking. I said, disregard it. But for the vertical asymptote, you got to take everything into account. So if it's negative 2/3, then this right here picture would be like, it'll be hard to see in your calculator, but I'll show you. It'll look like that. And then I would need, let's see, to make this into a 1. Well, it's gonna come up like this. The question is what the X intercept is. This is easy for you to figure out. Watch. See, the X intercept right here is 3. You see how 3 minus 2 is 1? If I can get the argument to be a 1, that's going to be the X intercept, is whatever makes it that way. The X intercept here was 1. So if I put a 1 right there, then I need the argument to be a 1. So somewhere in here, it's going to have an X intercept. It's not going to be the origin, but I don't know. So I can find that out pretty easily with my graphing calculator. But this is the vertical asymptote, by the way. Y equals log. Okay, 3x plus 2. 3x plus 2. Oh yeah, you see how it's bending left of 0. Yeah, everybody can see this bending left of there, and the y-intercept is in there, or the x-intercept is in there somewhere.
Couldn't you just do 3x plus 2 equals 1?
Right. Good. That's exactly right. Whoever said that, that's right. So to find the x-intercept, you take this and you want it to be 1. So 3x plus 2 is equal to 1. So 3x is equal to -1. So x equals -1/3. Yeah, that would be the x-intercept. You just can't see it in the graphing calculator. Unless I zoomed in, I suppose I can zoom in. You still won't get the actual value. Here, I'll show you another idea. This is actually easy to show. So okay, trace. I'm going to type in -1 divided by 3. So I'm letting x be -1/3, and if I get y to be 0, which I do, that just confirms it. Yeah, -1/3, comma 0. That's the x-intercept. So take the argument and set it equal to 1. Exponent form. You need log form, log base something. And you got 3 choices. 10 to 100. What's the base? 10 to or 100? 10, wink, wink. Hint, hint. This is base. This is base. Log base 10. Okay, argument equals. So you got to have something there and something there. What's left over is a 2 and 100. 50-50 chance. Actually, I know exactly what it's supposed to be. As I said before, these, to me, the way I remember it, if these are connected, they will not be on the same side of the equal sign. No, you don't put a 2 here. You put the 2 over here. I'm going to confirm it with you in a second. That means 100 is the only place 100 can go is right there. We'll check it with the calculator. Log base 10 of 100. Log base 10 of 100. I'm going to do the math thing here. Log base 10 of 100. Hey, it worked. So there'll be some problems that are going to ask you to do the, hey, convert these things. And I know on the exam or quiz, which there's no little quiz today. I don't have a quiz scheduled today, but there is one on Thursday. This will be log base 3 of something equals something. These are connected. You're not going to put the -2 here. I'm going to put it on the other side. And so this would be 1/9. Check it? Well, sure you can. I want that to be 3. I want this to be 1 divided by 9. Oh yeah, sure, it works. Okay, log base 4 of 2 is supposed to be 1/2. Oh, by the way, 1/2 power is the same as what? The 1/2 power. Or one. Say it one more time, Zach.
Divided by 2.
Yeah, it looks like it would be, just because why not? But it's not a divide by 2. Yeah, it's not.
Oh, I mean multiply. Right.
Well, okay, 4 times 1/2 seems like that gives you 2, but it's not a multiplication. No, the 1/2 power doesn't mean.
-2.
Yep, nope, right here. So right here, 4 to the 1/2 power can be rewritten as what? Not just 2. I mean, I want to rewrite it before you get the 2. The 1/2 fractional powers are radicals. Square root of 4 is 2. Of course it is. All right, you don't believe me. So let's do 8 to the 1/3 power. Okay, so you can't go 8 times 1/3 and you get some weird fraction. It's not true. I'm saying 8 to the 1/3 power, the answer is 2. I'm saying 8 to the 1/3 power is the same as the cube root of 8, which is in fact 2. Okay, I'm going to show you right here. Fractional exponents are radicals. You learned that from your previous course to this. Matter of fact, 2 previous courses. I'm just finished up with the baby beginning algebra class called 150. I just finished this up with them. Fractional exponents are all radicals. So you've had it in 2 classes. You just had to be reminded. That's all. Cube root. Okay, find the cube root, Jeff. I can do that somewhere. I think I'm under the math button again. No, there it is right here. Cube root. Okay, cube root of 8. I say it's 2. Well, of course it is, Jeff. Okay, 8 to the 1/3. That's, I got to convince you. 8 to the 1/3 is also 2. 8 raised to the parentheses 1 divided by 3. I'm saying that's also 2, which it is. All right, hopefully that convinced you. Okay, this is log base w of d equals x. And then this one goes the other direction. This would have to be 10 raised to something. Okay, is 10 raised to the 10,000 power 4? Oh, Jeff, I think it's this right here. Yeah, well, you're wrong. That's not right. That's silly. So, okay, that's the base that holds one of these numbers. One of those numbers. Well, it's got to be 4. Yeah, this is not right. Yeah, this got to be 4. Most students find it more challenging to take it exponent form and put it in log form. Most of my students, until they get accustomed to it. Most of you would find out, well, check it out. Make sure you write it right so it's true. Check it out. Like 3 to the 4th power is 81. 3 to the 4th is, of course it is. Of course it is. Oh, this is making sense. 5 to the, not the 1/5 power. 5 to the negative 1 is equal to the 1/5 number. 2 to the 1st is equal to 2. 2 to the 0. 2 to the 0 is equal to 1. 2 to the 0 is equal to 1. When x is 1, y is 0. That's what it's saying. When x is 1, y is 0. That sounds like an X intercept. Well, there'll be some of those in your homework to work on. There's no work to be shown. You either know, you don't. There's no process. So it'll be like problem number 3 through 36 by 3s. Well, it's just an answer. You either know, you don't, from the definition. And then there's graphs of e to the x. All you have to do is just put that in your calculator. It's called the, this is not a logarithm, by the way. This is an exponential function. We're back to exponential function right now. Exponential function using if there's a natural exponential function, there's got to be a natural logarithm, because those are inverses of each other. So let's see. Y equals e to the x. There's a couple different places to find e or e to the x on your calculator keyboard. You can find that calculator pad. E to the x, put an x right there. Zoom 6. Okay, fine. Table of values, plot maybe 3 points. Okay, that's not good. Plot 3 points. Okay, let's see. Okay, here's some smaller points. Okay, 2 comma 7.3. I'll plot 2 comma 7.3 like this. Here's your x, here's your y. 2 comma 7.39, I guess. Okay, well, see e to the first, or e, okay, x is 1, is about 2.71 or 72. Oh, e to the 0 is 1, sure it is, okay. And I'll do one more, so negative 1 comma 0.37. Okay, I'm going to plot those over here. So 2, and there's 4, 5, 6, 7, a little bit more. 1 comma 2.72. 1 comma 2.72. 0 comma 1. Negative 1. Okay. Jeff, it looked like it stopped there in my calculator. Again, it does not. So the inverse did the inverse, then you're swapping the x's and y's. So if you did the inverse, 7.39, comma 2, 2.72, comma 1, 1, comma 0, 0.37, comma negative 1. So if I plotted those in blue, let's do in blue, x is that. Okay, x is like over here, comma 2. Check, 2 points. Check, comma 0. Check. It doesn't stop there. And inverses have that characteristic that you guys all learned about probably the 4th week of the semester, that if you take the composition of the two functions, so we call this one here f inverse of x is equal to log. Okay, what's the base right here? Base e of x. Okay, so log base e of x. So if you take f of f inverse of x, or you do it the other way, f inverse of f of x, it always produces x, which is this line of symmetry. Oh, and by the way, up here, right here, log base e of x is the same as ln of x. So you see how I wrote that ln. I did lowercase. That's not a 1. That's, you can do uppercase is okay. I think your calculator, yeah, your calculator does both uppercase L and N, like log. It does uppercase for whatever reason. Notice the arguments are the same. ln right here and this right here. What I highlighted, that's what's the same. That's what's the same. Some students get the notation all mixed up. I understand, it's easy to do. Get the notation mixed up. They think right here, it's an ln base e. They think it's ln base e. No, it's log base E, log base E.
So Jeff, the red line you have there is log base e to the x, and then the blue one you have is f of -1. How would you say that? The invert.
No, my mistake. Here. Yeah, no, I started doing colors here. Yeah, once I started doing the first table in red, I thought about, I'm going to throw, and I threw you off for a moment. This table goes with that red graph right there. That table goes with the red graph. This table goes with the blue graph. Blue graph is actually the logarithm. This is the log curve, and this is an exponential curve. It's just these other ones you could do on your own. It's just graphing, just looking at the graph. You can put it in your calculator, check it out. Whoa, that's it, I guess. Oh, okay, think about transformations. Let's do that. Okay, so if I'm comparing this with e to the x, up here is a shift right 2 units. This is right 2 units. See how the 2 is away from where the x is? This is a down. This is a down 2. Okay, this one here. Okay, see in the argument, that's a right 3. It's a right 3. And so on. When you get into trig, my monster class, Math 27, is a monster class. Well, okay, just a little side note. You guys did good by picking this course over the monster class. I tell my monster class every single semester for the past almost 30 years, half of those students are going to be gone. Even in this, I would have thought even worse numbers would be gone because of this Zoom, but it's about half. I'm down to 18. I was at 34, just like here. Now I'm down to 18. They can't keep the pace, and they didn't believe me. That was all review. We go fast. You guys did good by picking this one because we go slower. But you guys are going to pick up probably Math 58, which is the trig. Most of you will. In the trig, you have trig functions. And in my monster class, I continue to talk about the transformations. I use the same language: left, right, up, down, reflect, all the trig stuff. It's a continuation. So right now you're using it in the logarithm and the exponential, using that same language. They're way past you guys, of course. They're into their trig. They're about halfway into it. You know, we only got what, 4 weeks left or 5 weeks left. That's it. 4 or 5 weeks of instruction. That's it. That's it. Okay. Let's see. So anything for me that you want to ask before we say goodbye? Today is Tuesday. Yeah, I guess we'll see each other on Thursday. That's my plan. Okay, remember Bonnie's not around, so you can't go to her room. I'll stick around. I've got about 20 more minutes. If there's questions, homework questions, anything you want to talk about, happy to do that. Otherwise, see you on Thursday.
Hey Jeff, I think I'm just having a hard time understanding or wrapping my mind around the full concept of the difference between the continuous, oh, of course now my brain's going to decide it doesn't want to work. The continuous compound for interest rates.
Yes.
And if you could just go over it just slightly real quick. For some reason it's just not sitting and I don't know why.
I'm going to look at here. Oh, right here. Let's do this. Can you see what I'm seeing? Yeah, the most frequent compounding, which requires us to use a natural log. Okay, blah, blah, blah. So somehow continuous compounding has something to do with natural logs. Commonly used in finance. Okay, in multiple periods in its time. Okay, that's still not telling me what I'm showing. Continuous compound interest. What does that mean? Even right here, it says interest rate, yeah, the compounded monthly, quarterly, semi-annually is the most common. I'm still not seeing where it would be used in real life. Okay, that's not going to help. I know what your question is. I'm curious as to. Yeah, but nobody uses it. Okay, fine. Okay, let's see what else. That's just a definition. I'm having a hard time even finding it. Let's see. No, I don't want that. Let's see Wikipedia, like it's the Bible, but it's not. I don't have an answer. Isn't that weird? Okay, so I don't have an answer for myself. For you, here's the difference. The formula looks different. And I would like to think your calculus instructor, when you get there, will demonstrate how the formula that starts off this way. Here's your formula: A equals P1 plus, let's see.
Or see. So I have that for the compounding period per year, as it shows. You have it in here as well, and it's in the book. And then the continuous compounding is that the A equals the PE to Is that RT, the exponent of RT?
Yeah, so this is,
Okay.
but if it's continuous, that means n is getting to infinity. So again, you'd have to say the limit as n goes to infinity. Then this here heads to this here for some magical reason. Your calculus instructor will usually demonstrates that. For you, you're just looking at the word problem and say continuously compounding, then use this one. If it's not continuously compounded, they'll say compounded daily. So use this one, you put 365 there, 365 there. 15 years, okay, time is, it's always in years. What if it was a half a year? Well, like 6 months, and you would put in 0.5 here for t. Interest rate, you got to put it in decimal, not percent. But down here, this is compounded continuously. So the E is constant. E is going to be this number in your calculator. P is always called principal. R is your interest rate, and T is how many years. So it's just a difference in formula. Where is
Okay,
it
so
used? Yeah, I don't know.
it's just plugging everything in and getting the answers from there. Okay. Okay. Yeah. I was trying to figure out because I understood more of the compounding per year part. I didn't understand how we get to the continuous compounding.
Yep, the connection of here to here.
Okay.
How is that? That's in calculus.
Okay.
You're just using a result that for now, and where even I can't even find where that's even used in real, like Richter scale. No, it's not used in the Richter scale. It's not a logarithm.
Okay.
So.
Okay. Awesome. Yeah. My next go was going to be definitely was going to be Google and try and see if I could find it through there. So.
Yep.
Thank you. I appreciate it.
Okay.
All right. Have a good rest of your day.
I will.
You saying bye?